as possible. All right, step 4. This is the oxidation phase. So what should we see happening here at some point? Oxidation involves loss, oil rig. Oxidation involves loss, reduction involves gain. So we're actually going to see both. When something is oxidized, something else is reduced. So what we will see, I'm going to clear this out here. What we will see is that our first electron carrier, NAD+, remember that? NAD is going to be reduced to NADH plus H+. Now at the same time, this P-gal is going to be reduced. And we're also adding a phosphate to it. Actually, this oxidation phase here has been compressed. There's actually about 3 reactions occurring here. So NAD is going to be oxidized to NADH, reduced to NADH, and the P-gal is going to be oxidized to this 3-carbon molecule. What we're not seeing is the fact that the hydrogens and electrons came off of this molecule here. So we're oxidizing this to this. Same thing is happening over here to the other P-gal molecule. The last step, the dephosphorylation phase, again, is several reactions that have been compressed into one. And what happens here is ADP comes in and pulls off the phosphates. And our final product then is what? We get 4 ATP, and then we have 2 3-carbon molecules down here. And what molecules are these? These 3-carbon molecules. Pyruvate, pyruvic acid, either one is fine. Is there a way that we could write one single equation for just glycolysis, kind of like we did for the entire cellular respiration? Taking the reactants on one side, producing products on the other side? Go ahead and try and write that down. What do you think that would look like? Think about what you're starting with, what gets added to the reactions, and then what you get at the end. In fact, I'll even circle the products for you. You get some, but we're going to see that we get ATP in the citric acid cycle and electron transport too. So you can't say that just to refer to glycolysis.
But you have to know about that quite extensively before you can understand this completely.
So what'd you come up with? If we were to write one single equation for glycolysis. Obviously glucose. What else are we using? What else are we adding into the recipe? ATP. 2 ATP, in fact. We're adding some phosphates. A pinch of NAD. Anything else? And what do we get at the end? We get 2 pyruvates. We get 4 ATP, 2 NADH plus H plus. And we also get 2 ADP. How's that look? The reason I asked you to do this is I wanted you to think about the reactants and the products. Let's look at our totals here. Thought I had these tables included, but maybe I don't. So we know that we use ATP. We know that we produce ATP. We're going to add to this chart later, so yeah. Maybe you do have this chart. Looks like this. Dan, what page is that? 29, if you have the packet. So how much ATP did we use in glycolysis? 2. We're investing money. We want to make some money, so we have to invest some money. We have to get a return on what we've invested. How much ATP is produced in glycolysis? 4. That's for every single glucose molecule we get 4. So what's our net total? If we didn't make 4 profit, we invested 2, we got 4 back, so how much did we make? 2. How much NADH did we get? 2 molecules of NADH. There we go. What about FADH2? Not involved yet. What we will see eventually is that the NADH, it's picked up electrons and protons. Those protons and the energy in those electrons will be used in the electron transport chain. So even though we only got 2 ATP, we've collected energy that will be used to make more ATP later. And that energy is in the form of NADH right now. Okay, I want you to take about 5 minutes or so. I want you to go through those 5 phases of glycolysis, thinking about what we started with, what we end up with, looking at how the number of carbons changes, if it changes, what the energy yields are. What else did I say to look at? Oh, oxidation and reduction. Right, because the ATP is giving up a phosphate for here. Down here, the ATP is coming in to pick up a phosphate as it's taken off of that molecule there. I'm going to save myself some time. If you can, you might want to write a written summary of what's happening. You don't have to, but that might be a good way to, another perspective to look at this stuff. There is, I don't remember what it is right now.
Yes, Dan, I was wondering, does the glycolysis metabolism correlate with the lipids and the protein? I'd like to know that. Because you talked about lipids and glycogen. That's that first step. First option. I've heard this referred to before a couple times in my life as a Krebs cycle. Am I correct on that? Or
Say that again?
have you ever heard this referred to as a Krebs cycle?
Not this.
No.
This is something totally different.
Okay.
We'll talk about the Krebs cycle in a little bit.
Okay. Are you in your office today?
I'm scheduled to be. There's some family stuff that's going on, so I may have to duck out of here early today.
I'll touch base with you tomorrow the next day. Hope everything's all right.
I just did that just to show you that it's different. Just to show that it's different. It's still in 6 carbon. Yeah. What's happening is there's rearranging of hydrogen and oxygen occurring out here. That's an infinite dose. Oops. Question was asked, if this is glucose 6-phosphate and this is fructose 6-phosphate, why is the phosphate in a different place? Well, technically it's not. I just put it over here just to show you that this molecule is going to be a little bit different from this one. I think for next year I'm just going to keep it the same and maybe not even get into the fructose 6-phosphate thing because I think it just adds another little layer of confusion. But basically it's still on the number 6 carbon. But the difference is we changed some things around up here with regard to the organization of the oxygens and hydrogens that are attached to those carbons. Okay? Any questions about this? So, for every single glucose molecule then that goes through glycolysis, there's the potential to produce a net of 2 ATP, and that's what we look at when we talk about our totals. We look at the net total of ATP. And there's the potential to produce 2 NADHs. Remember, NADH is the same as NADH plus the H plus. Now, just to kind of get you maybe thinking ahead, there's enough energy in one molecule of NAD to produce 3 ATP. And this is something that happens in electron transport chain. There's enough energy in that NADH, one single NADH molecule to produce 3 ATP. But we have 2 NADHs. So what's the potential for ATP production here? 6.